In fact, now if I do the packlet install, is it sufficient that I've installed the packlet here? Could you not type right in our ear? Okay, so this is now running it, seems to be working. Okay, 40 kernels up and running. Okay, I don't entirely understand this table, but as I said, okay, what does the blue mean? Is the black exact?
No, the blue is exact. And if you hover over one, you get the rule, the signature.
Is this thing symmetrical? Yes, it
Yes.
is. And what's the ordering across the top?
The complexity, I think. The total, it's the total rule length. It's the length of each part.
Why does it start at 1.5?
Because the smaller ones, you can change the min max.
Okay, so most of what we're interested in I don't understand. Where's 2? Oh, I see. 2, 2. But most of these, it will be completely uninteresting.
Right. So you'd want to limit based on the rules for being interesting.
Did you just edit initialization, Max?
Yes, I put new max connected atoms in it.
Okay, all right. Okay, so but this table is not for the new connectivity information, right, Ed?
Correct.
Okay, so this table is not in fact correct.
However, filling in blanks for many of these entries would take.
I'm not talking about filling in blanks. I'm talking about the particular thing we need, which is the case where we're looking at this connectivity stuff, right?
Right.
But this is without the
I don't have a simple estimate for those. I can get one though, but it would take a while to compute each item.
Okay, well, that's still relevant. But now, I mean, with this table, okay, so I need to figure out what I'm going to show from this table. Because I want to show the most relevant pieces from this table, which is definitely not the whole thing. And the blue, so even in a thing like this, 112 to 18, you have an exact version of that. Is that right?
Yes, since nothing can move, it's the standard order count, Bell B.
So wait a minute. So you're telling me that in the particular case, I just asked you about this case, and you told me it wasn't possible.
No, I don't.
Okay, so what you're saying is that the case, for the case 1.
This is the opposite of what you were asking before.
1M goes to 1N, right?
Mm-hmm. It's bel B n plus n.
Okay, so explain that. So that's just permutations of.
No, it's not permutations, it's standard orderings.
I see.
And since nothing can move, if it's a standard order, it's a.
Is there a connectivity story here or not?
These are not necessarily connected.
Okay. Okay, so to generate this table, is this a fast table to generate or not?
Oh, yeah. 1 second.
Okay. But this is, and so how do you know which ones are exact?
If both, if there's no permutations applied, then it's exact.
Okay, but there are some values which are exact even regardless of that, right?
No, all the ones
not
that are
in
exact.
this table, not in this table, but you know exact answers.
Oh, yes.
Okay, so we need to fill in the exact, I asked you this like 8 times here. The exact answers we know, I would like to get those.
Right, it's going to be the smaller cases with total length less than 10. We do know, and it's approximately the same as the values there.
Okay, but which ones? Okay, so the cases with less than 10. All right, so what are those cases, right? So we've already got, let's make a list of what those cases are, right?
Well, it would be things like 2-2 to 3-2 has total length.
I know. Right. So okay, can we make a list of everyone we know that has total length less than 10, please?
It would be all of them.
No, it's not all of them. Okay.
The version of the code, my most recent version, basically will do that.
Ed, do you understand the question I'm asking?
Yes, I do.
Okay. It's a trivial thing.
No, it's not trivial. It is not trivial. Don't say it's trivial.
This particular
Do not say that it's trivial, because it is not.
Okay. The sum of n.
It's not trivial.
Okay.
Stop saying that, because that's one of the things that's making this so hard. You keep trivializing the problem.
Okay. The particular thing you just said, namely the total is less than 10, is trivial, right?
No, it's not.
But the total is just n sub I times k sub I, the sum of n sub I, k sub I.
True, but calculating them all is non-trivial.
Calculating all what?
Calculating the exact counts for all of them is not a trivial problem.
I understand that, but knowing which ones are worth trying to calculate the counts for is trivial.
They can all be done, and
no.
day and
No. You're not understanding. You're not understanding. I simply want to know what are the candidate rules here, right? The candidate signatures whose total is less than 10. Do you see what I'm saying? Let's just
right.
the partition
You just
thing.
modify this other table here and get the total rule length. You just basically pinned the multiplication to get the total.
Wait a minute. What we've got is someplace I had this here. Here. I just had computed, well, it's trivial there. Okay, look. Okay. Because I want to get the ones that aren't just, I want to get things like 1, 2, 2, 2 goes to whatever, right?
Right. Okay. Just do like tuples of range 9, comma 2, that will brackets around the 2, and subsets 2, and select.
I don't need brackets around the 2. This is just giving pairs like that, right?
Right. And then we'll get pairs of pairs.
Okay, by doing what? By doing
subsets 2, or tuples. It doesn't matter because there's symmetry. We as well just do. Yeah, tuples 2 is fine.
Okay.
And then sort them by the total flatten.
But that's only going to give. Okay, that's not giving these cases here.
Oh, those two. Then we'd make a separate case for 3. And we could do a cases for 2.
So wait a minute. Hold on a second. So let's just select on this with total flatten of that is less than 10, for example.
It's actually less than 11.
Well, less than or equal to 10, we'll do the same thing. Okay, so this is the ones where we can reasonably go blah, blah goes to blah, blah. Okay, so we have to pick out the ones of these that we actually might care about. Because many of these are, so one thing we want, I think for these, we want the left and right-hand side second numbers to agree, right? So we want cases of this, which are of the form right, like that. And then we want select that hash sub 2, 1 is greater than hash sub 1, 1.
Because of symmetry, yes. Greater than or equal, because
well, we can do greater than or equal, but
no, it means they need to grow.
Yeah.
The equal is not good enough. It actually needs to be larger.
Okay.
Okay, so these are the cases that we care about. 1, 2 goes to 2, 2. I don't think we care about the 2 ones. Do you agree, Max? The k equals 1 cases.
Yeah, I don't think they're interesting. Right, the other trivial or disconnected.
Okay, so let's enumerate the ones that we actually do care about. 4, 1. No, we don't care about that one. 1, 2.
You don't want anything that ends with a 1.
No, I want one thing that ends with a 1. Okay, these are the ones I care about. So how do we get the enumerations for these? We want the total counts for these.
Right. Something weird happened because you've got 1, 2, 5, 2, and that's a total length 12. Oh, I think we needed total of times that rather than just total of flatten. but it's pretty much the same thing.
Well, but let's get rid of that one.
It's one you'll be able to do, though, definitely.
Okay, but let's order these in the correct order, though. So let's order these by sort by, and then what is the correct thing?
Total times add blat.
No, at.
Okay, right.
Okay. Okay, so those are the ones we care about. So now what we want is the total connected rules for each of these. And then we want to estimate the number of rules for bigger ones. Okay, so on the table we want to give to estimate the bigger ones. I mean, we've basically got an estimate down there.
Right, and I've sent code for doing a better estimate.
Okay, well, fine, but we should try a better estimate. But let's figure out what table we want to have here. Because also we don't have the cases, the triple cases, right? The cases where there are different. We need some of those.
We can add those in. However, the triple cases won't have everything having the same argument length in the last part.
What do you mean?
The tuple sizes need to vary for a three-part case.
Which tuples?
The signature is basically if all the tuples are the same length, then you can only have a two-part rule.
I'm totally confused. I mean, the case that I'm looking at is something like, you know, 1, 1, 1, 2 goes to 2, 1, 1, 2, let's say.
Right. The tuple sizes are different in that case, which is fine.
What tuple sizes?
You've got tuples of size 1 and tuples of size 2.
Of course.
Okay.
That's what that signature means.
Okay.
I mean, that's what we want. But I want to know, I mean, I want to enumerate. I assume we can enumerate in a case like this.
So we go up to there and we, instead of 2 of those tuples, we do 3.
Well, I understand that. I'm just checking that this will work, though.
Okay.
I do this. What? What happened? Oh. Stupid. Is that really right?
They're probably all non-connected.
I see.
Really? I mean, if they all ones, for instance, why would they be not connected?
I'm suspicious that I don't think this is working right.
Yeah.
If you take out the 1, 1, they probably will have
this 1, 1 here.
Right. I guess take out the 2, 1, see if that's what's killing it. Let's see, we could do 1, 3, 1, 2. That should still work.
1, 3.
Well, and 1, 3, 1, 2 on the other side, yes. Basically a 3-part rule.
What are you suggesting here?
On the left-hand side, 1, 3, 1, 2.
And on the right-hand side?
Yeah, that's fine. Yeah. And you could probably take out the 2 as well for limiting. And
it's quite zippy. Okay. So it's another case we can do. I mean, I doubt any of those rules are interesting. I think those rules have to be trivial because they just
Yeah,
have
they have to be. It will destroy all those 3 edges and then it will stop.
so the question is, what is a interesting 3-part rule?
I don't think there are any. I think you have to use both sides, both arities.
Well, you can put something on the right-hand side which is never used, but it would introduce some structure to it. That might be interesting.
Fine. So the other way around of this, but it's not. That's not going to work because 1, 2 goes to 2, 2, and 1, 3.
Yeah. Of course, 1, 3 will never be used, but it's. I mean, it will.
Oh, we could do this
something
even.
there.
That there are none of. Okay, let's try 2, 2. There are none?
That doesn't look correct at all. Because if all of them is, in other words, if all the atoms are 1, it should work.
I would think so. So that would be the rule 1, 1 goes to 1, 1, 1, 1, 1, 1, 1. What's wrong with that rule?
Try the connected Q thing on it.
Yeah, good idea.
What is the thing called?
Connected Wolfram model Q. Well, try canonical. This canonical Wolfram model.
Oh, right, because the 1, 3 has to be before the 2, 2, because it has to be 1, 3, 2, 2 on the right-hand side.
Why?
Because the longest tuples always appear first in a canonicalization.
Well, no, actually, it's a bug on our side, because when we canonicalize it, we should. I mean, we still need to return everything that is requested.
Yeah, this particular thing is a goofy way. Okay, so let's say 1, 3, 2, 2 here, but that's not. We should sort that ourselves, right?
Yes.
Okay, so let's put that in the code. I mean, we enumerate Wolfram model rules. Better be putting its signature in canonical form. See what I'm saying?
Actually, what should we do here? If we should either return them which are not a signature requested, or we return them which are not canonical.
No. Put them in canonical form. Absolutely, without question, put them in canonical form. We don't care what the signature is. The signature is its own separate thing.
Okay. Well, then we just sort the signature on the input.
By the way, is this SW Zoom or is this a different Zoom?
SW.
I asked Jonathan to join us. He didn't.
I've been here for the last half hour.
Okay. Well, you didn't make your presence known, as they say.
Sorry, no, I didn't want to interrupt.
Well, thank you. Okay. All right. Okay. Is it easy to we've got two different things. One is the limiting of the symbol here, and the other is the canonicalization of this. So if we could figure those out. But now, Jonathan, you had something. You're probably about to go to sleep, so we need to talk to you about well, okay, Max and/or Ed, can you figure out this question that or I could go to a separate Zoom session with Jonathan if that would be better. Hello.
Which question are you talking about?
Yes. Which,
okay, we've got two things. One is canonicalizing the signatures, so we don't have this.
Should be
right. Yeah.
That should be what?
That should be trivial.
Okay, well, we should do it. Okay, and the second is getting the limiting of the symbol correctly, right? The limiting of the number of elements, which didn't.
Max is working on.
Yes, I already did it. Actually, it's
Okay, so give us that code. Give us that code, and then we'll put that in.
Well, the code is in the same as the old code. It's in the initialization file.
Okay. So you just put that in. Hold on. So let me go there then.
Yeah, that's why I changed it.
Well, that was half an hour ago.
Yeah.
Oh gosh.
Well, I told you I put it in.
I'm very confused. I know, I was not paying attention. Okay, so is this, now you put in max connected atoms? Wait a minute, there are two versions of max connected atoms here.
Why?
Oh, no, I see, it's type.
There's only a new version, yeah.
Okay, all right.
But there's 3 types.
What's the default?
Automatic.
Okay, all right, fine. So this is going in here. Where do we put it in? Oh, it has to go in here, right? And then we flow through okay, so if S, how do we, where do we put it in? Where do we put in the max connected atoms thing? Where do we insert that value?
I would probably, in the upper piece of code, his code would substitute for the automatic based on the.
Oh, I see what you're saying. This automatic, I see what you're saying. I understand what you're saying. Here, for the automatic case, that would say max connected atoms
signature,
comma, automatic. Right? And then this would say of, and then this one here if S is not equal to automatic, okay, so it'll never be automatic in the end. Okay, so this is the case for an integer. And here, it's the case for automatic, or none, or all.
Well, it's not enough because connected Wolfram model queue should also take that as an argument. So we do need to pass it.
Okay, what's the best way to...
Actually, we need both. Because these are independent things. We might have fewer atoms, but still want.
Right, and then you do min of S and Max's number.
For what?
Just in case you only had an alphabet size of 2, you generate Max's number, which might be 7. But
okay,
then
hold on. Here we want a type, basically, is what you're saying, right?
Yes.
Okay. And here, what are the options now? Oh, that's that thing with, okay. So here we have a type. Okay, so how are we going to give that? So you can give, maybe we should put them in a list. What do you think? And we can default, if they're both the same, to being, what is the type then? The type is, what's the default for the type?
Automatic.
Okay, so this type, no, but I mean, if you just give S, this type can be automatic, none, or all, correct?
Yeah.
Okay. Okay, so now down here, what do? We say S, we give the S, and what do you do here? We do the select of that. But how do we do the S?
What do you mean? It uses S already.
No, I understand, but Ed was saying that it needed something else.
The bracket should go after the function. One symbol to the right.
Okay, fine. So that's enough there. Okay, so now the cases we need to deal with. The default case gives max connected atoms and automatic, correct?
Yes.
Okay. The case of a pure automatic there, a pure type there, gives max connected atoms and the type. Right?
Yeah.
The case of an integer there gives automatic there, right?
Where is this? You should use that integer somewhere. Probably instead max connected atoms.
All right. Okay, so now here, oh, what about that sorting? How would you do the sorting?
Well, just sort the signature at the beginning.
Here? In here?
Wait, let me see. I would say just put the V's and define sort of signature there.
How do we do the sort?
Okay, that's for Ed.
Ed, how do we sort the signature to get it canonical?
The negative last element on each side.
What do you mean on each side?
Left-hand side, right-hand side.
Okay, so, but the signature, okay, how do we check that the signature has the right form? What is the signature is supposed to have a top-level rule in it, right? Right, the signature is supposed to be a rule, correct?
Yes.
Actually, I'm thinking if the better way to do it is to essentially produce a rule with a signature, canonicalize it, and then extract the signature of the result. Because this way, what we do here would not depend on the canonicalization code.
I don't think that helps.
That's a good idea. Let's say, okay, so here what we're doing is reverse sort by hash comma last. Right? Is that correct? Okay. All right. How certain are you that this is correct? Because I'm going to be using this immediately, basically. So, for example, you say, if I give, this was a fairly fast one to do, right?
It is now.
Well, we didn't unit test it, at least not the last version of it.
I agree.
So I don't think I can guarantee that it's correct.
No, we need tests for this. We need tests. We don't have tests here. We definitely need tests. Okay, so let's just write the documentation. Generates a list of all canonical connected Wolfram model rules, specified signature. Signatures are given in the form NIKI. Well,
I just realized something.
That's never a good sign. Yes, Ed.
So Bell B is the total number of standard orders. For the connected case, we want to limit those by the atom size. And we can get that from the mask, whatever I called it, mask something. Bell mask radix.
Okay.
And we would select only the ones where the mask was equal or smaller to the atom size. And then the radix part, which is included with that, gives the total count for each one. So we'd basically apply times to all the radices, and then we'd get a total count of the raw thing for possibly connected standard orders.
So you mean without enumerating them?
Right.
Okay. So you're saying if we say count Wolfram model rules, that we will have a different, that you can have different code?
Yes. And we could improve the estimate to only include those that could be connected.
Okay. Well, I'm going to leave you to do that. Okay, tomorrow.
Okay.
But then the table that I need, right, is these cases and any other cases that are within range.
Mm-hmm.
You know, small cases which have growth in them. Okay. And which also don't have things that can't be computed, like
well, these are the easy cases. You can do harder cases now. It looks like you could do something like 3.2 to 4.2 now. I'm pretty sure you could finish that one in like 10 minutes now.
Okay.
So then that's worth trying with the new enumerator.
Okay. All right. Okay, fine. I mean, then that's okay. Let's finish the documentation here. Okay. This is allows only S distinct elements. Generates all possible rules with a specified type of connectivity. And then we have the final case. Let's see. Oh gosh, why is it doing this? Okay, so what is the first thing here? This is the S. No, this is distinct elements. What is the difference in the two types that we give here? Do you understand what I'm saying? If I say automatic all.
That's more a question for Max.
Yeah, I know.
Well, all means it's how much they're connected. All means right-hand side is connected. Automatic means...
I know what they mean. I mean, I'm just saying, what does it mean if you say all comma automatic in this specification here?
I don't understand the question.
Look at the syntax. We can say automatic comma all. The syntax allows that. What does it mean?
I thought S supposed to be an integer.
We allowed the case. You told me to allow the case where S can be like automatic there, independent of what the type is.
Oh, I see what you're saying. Okay. Well, then we would essentially have an unreasonable number of atoms which have nothing to do with... Anyway, I mean, we could definitely do it, just that it's not very meaningful.
Okay, all right, okay. Okay, so the cases that we have are all require both left and right hand sides to be connected individually and together, right? Yes. Automatic require left hand side to be connected and connected to right hand side.
And also there's a subtle case. If the right hand side is disconnected within itself, and also there are pieces in it which are not connected to the left hand side, it is going to treat that case as disconnected.
Okay, well you can say, okay, what does none mean? Do not constrain based on connectivity.
Yeah.
Okay. Okay, so Ed has a separate way of doing this and will give us Bunch of estimates. Okay, I think
Actually,
that's
you could probably do all of those cases there with this new version in less than 2 minutes.
well. So, for example, you're saying 1-3 goes to 3-3.
Yeah, that should be pretty fast now. Oh, well, it needs to be a rule. Yes.
Let's watch the big dashboard. Wait a minute. Why isn't there anything parallel? 40 kernels running.
Maybe it just hasn't updated. Oh, you can start seeing some of them are growing.
Are you sure?
Yeah, you can see slivers of green on various ones.
But those are, but I
Already
think,
go this way.
You might as
why?
well ask John the question you were going to ask him.
What?
You were going to ask John something?
Jonathan. Yeah, but wait a minute. Why is this not doing? Let's see what happens here if we. Come on. 40 kernels running, it says.
Well, they're always running, even if they're not evaluating anything. But it looks like the busy indicators are broken.
Well, let's see whether the activity monitor shows behavior there. What is it doing? Oh, maybe now it's trying to format the output. That's a bit of a mistake to have. Oh my gosh, that's quite a long. Okay, so then this.
346,000.
Okay, so this is 3 to 3, 3. Well, I'm pleased that we can get this.
That was an overnight run a couple of weeks ago.
Okay, so that's the number of connected ones. So we're going to give the ones that have, okay, I need the formula here, this formula here, for the maximum number of distinct elements in the left connected, right? See what I'm saying?
Yes.
I think what we want is a table. We'll just have a multi-column table which just lists a few of the interesting cases.
You may as well copy the 1-3 to 3-3 over there.
Where is the 1-3 to 3-3?
It's in the code you just ran.
No, but I mean the formatted version. There it is. What did I just compute? I computed 1-3 to 3-3. Why does that say 2048 there? It's complete nonsense.
I think that's for binary.
Oh, I see. Okay. Okay. All right. Well, now we got a big search to do on those. But Okay, so the issue now, so I've got some previous results that are wrong. So I need to fix those. Okay, I think what we want to do, Ed, is to make a table, as I say, just to think of it conceptually as a one-column table that just lists rule. You see what I'm saying? Rule together with.
Yes, I can do those, and I guess mine will be about 20 times slower than what you've got.
Well, that's silly, because I mean, I might as well do them. If you just give me some code, or give Roger Dooley some code early tomorrow morning, he'll run it on this machine. Okay.
Okay. Oh, basically, it would just be mapping that to your list there, change the rules.
But you said you've got a way to do the counts without explicitly generating everything.
Oh, I can do estimates.
Okay. All right. Okay. Fine. But then Ed. Okay. First point is just give me the list of all plausible ones, including the triple ones.
Mm-hmm. Okay. Okay.
Okay. So I mean, this one. I mean, I can run these overnight easily enough.
Actually, it might be good to run a bigger one just to see what happens. Like 2.3 to 3.3 would be very challenging. Well, it would have been impossible, but now I'm pretty sure it can be done. Yeah, that's a reasonable overnight run there.
Well, it's predicting it will finish.
Well, it's predicting incorrectly because it's not uniform.
I understand, but that's predicting it will finish in 5 minutes or something.
And it keeps increasing, which means it's not correct.
All right, I was expecting this to take overnight, but I'm pretty sure that that would finish in less than 20 minutes. So I don't know anymore what this can do.
Okay, well, just get me the list of plausible. Oh God, don't tell me this is unstoppable. Oh, that's super annoying. There's something wrong with interrupts in this case.
Yes,
Okay.
stopping over the network usually doesn't work for me as well.
Well, do I have a bunch of zombie kernels running on these other machines?
Well, definitely.
Oh, come on. Well, how do I clean them up?
Well, you go to that machine and then you do
No,
kill all.
no way. No, I'm not doing that. I mean, we can do that with the process system. Let me just send mail.
Well, how else do you want to do it? I mean, just SSH there, you say kill all.
I know what to do. I know how to do that. I'm just refused to do it. I'm going to have a piece of code that does it.
I'm actually curious if you do closed kernels, would it do that? I suspect not. Well, but how does it know if those are zombie kernels or if these are kernels which are used by somebody else who connects into your computer to use part of your kernels?
Because it has links. These kernels.
Not anymore. If you kill the kernels that you're launching them, you don't have links to them anymore.
Okay, well, let me ask Roman that question. I didn't kill the kernel. If I quit a kernel that controls parallel subkernels.
But you might have a timeout. If the master kernel didn't communicate with them for a while, they might kill themselves.
I don't know. I kind of think Roman thought of this years ago when he built all this stuff. All right. Is Jonathan still there, or is it that because I would like
Yep.
to? Okay, I think we are done with the stuff. So Ed, the thing that would be super useful to me is just to get ASAP, so I can run it. If you can still do it now, to just get me the list of the plausible things to run overnight. Okay, and I will run them. Ed.
Okay.
Just the plausible things, that plausible and interesting, like they grow, they're not. You understand what it takes for them not to be sort of
Not entirely. That's more Max, something
okay.
Max does.
Okay, so Max okay, we've got this estimate, which is the sum of NIKI
But go
divided
ahead
by
and
this.
send me that list.
Okay, but yeah.
I'm not sure when a 3-part rule is interesting.
Okay, Max, explain when a 3-part rule is interesting.
Well, if there is one part on the left-hand side and 2 parts on the right-hand side, such that one of the arities match and the other doesn't, that could still be interesting.
Okay, I think I understand what that means.
In a sense, it's like so it does something which is never used, but it's still interesting to look at, after the result is obtained.
It's like a what?
So function.
So.
Yeah.
Okay.
But for tonight, you may as well just do 2-part rules.
No, because I want to do everything I can get to work. That's the point. That's I mean, if I can, because I'm also going to use these. These are what I'm studying also.
Well, if we can somehow enumerate signatures by complexity, then you could just run, like you start running them and you keep saving results as you do it. And then
But might be best for Max to pick 2 or 3 3-part rules.
Let's just do it right now. Let's just do it. We can do it. Okay, so just a minute. Let's just. Why does that thing open up when it evaluates? Okay, so then what we've got here is we've got rules that have what properties? We've got to have that this quantity, right? Let's just do the sum of NIKI, right? So, guys, we basically just want to have, let's write down the conditions. So we've got, we're going to sort them by this, actually, we could presumably even compute this quantity. We could just sort them by Bell B of this thing divided by the product of the NIs. Isn't that right? So we'll say LHS arrow RHS. And then we say, let's have an S0. No, it's all of them. So it's times triple at LHS. Does total, yeah, it's total. I mean, this is kind of weird, but it'll work. Okay, so this should say estimate. LHS 22 arrow 32. Okay, do you agree? So then this wants to say times at that. No, product of those factorial. So it wants to say factorial of that. So division. And there we want to say bel B of that. So that should be an estimate.
Right.
Of that. So we can say n of that, but it doesn't really matter. Okay, so this is
Or round.
yeah, it doesn't really matter. Round is much slower. Okay, so now we generate 4 tuples of numbers. Okay, so we make a table in which, so we might as well make a table by arity, right? So we make a table of I arity goes to J arity with J running up to I. Is that the right way around? I goes up to whatever it is, 6 or something. J goes up to I. No, J goes from
6 other way around.
I goes up to J. J goes up to 6. And then the arity goes up to 4, let's say.
Can you do it in that order? Or should you do J first?
I think you do J first. Okay.
Why arity only goes to 4?
I don't know, that's what I'm doing for now.
Okay. That was suspiciously fast.
Oh, well, this is just,
Suspiciously wrong. Look, 1, 1 goes to 6, 1 is sorting in front of 1, 1 goes to 5, 1. Well, of course,
oh,
the estimate goes.
Yeah, that's true, actually.
What's true?
Because there's more permutations that can be eliminated.
Oh, wow. Okay. All right, actually, we can do J plus 1 there if we want to do. Oh, no, it's the other way around. J minus 1. Right, that is the increasing arity case. Okay, so those are the ones of the form. So now the next thing we want is 2 arities. Okay, so those are the 1 arity cases, right? And I think what we want to say here is select. Oh, those have the same arity. So we want to select the cases that don't have an arity.
I would also add a select where the estimate is less than 100 billion.
Okay, well, let's say select percent est of hash. Well, that's.
Why do you need to do that? I mean, we could just keep them running until the morning and just keep as many as we can get.
Yeah. Okay. Okay, but even the ones that are bigger, we will get, so let's say 5, 4 to 6, 4. For my purposes, for my table, that's fine. 10 to the 35 is fine. If I just write that down in my table, approximately 10 to the 35, right?
Yes.
So I'll give the exact ones, and then I'll just do tilde, tilde, and then the bigger ones.
Mm-hmm.
So we'll get as many as we can get exactly, and then we go for the other ones. Okay, so now that's the case with a singularity. Okay, so now the next case is, so Max claims that the next interesting case is JA goes to, and then KB, correct?
Yeah.
Okay, where that arity there, well, K goes up to what? Anything, principal. Say 4, for example, and B goes up to,
Well, I guess it depends on what you mean by interesting, because the behavior it will produce would be the same as if you didn't have this KB. But the final state would be different.
I don't think that's interesting.
In other words, if we don't care about this, if you're looking for the universe, we don't really care about this case because the causal network will be the same.
So let's not worry about this. Okay, wait a minute.
Okay.
Wait a minute. But the, oh no, that's K, actually not K, it's K there, but the K prime prime arity relations will never interact, will never, okay, so you claim the next interesting case is,
So why aren't you using prime symbol?
I'm doing the wrong thing. I'm doing the wrong thing here. Don't worry about it. I'll fix this, okay?
Okay.
Okay, look, we can overgenerate this trivially with the estimate thing being so what we want here, and I mean obviously we can have pairs of rules after this, but what we where those are completely independent. The canonicalization of the pairs of rules is completely independent.
Yeah. Well, almost.
Okay, what do you mean almost?
Well, what if the two rules are identical?
Wait a second. Your claims here aren't correct if there are multiple rules.
What do you mean?
Well, another rule could eat up K double prime arity things.
Yes. Yes, that's true.
Okay.
Well, a lot of things are incorrect if we have multiple rules. For instance, it could decrease the size.
Indeed. For a single rule, Right. So we will be looking at those, separately. Okay, but for the increasing ones, shoot, yeah, we should probably enumerate a few of those, because because then we have to say for multiple rules, for cases of multiple rules, there can be individual rules that decrease the number of relations. Yeah. Or that produce relations with different arities. I'm sure that Jonathan has now fallen asleep. He better have done.
Unfortunately not. Should I?
No, because we could talk about your thing. Okay, I think we're done with what we need from Ed. I think we understand what we need here, and I can do whatever run I can do. All right, let's go to Jonathan, because he's been waiting a long time. So Ed, thank you, and Ed, you've got the stuff with the. You said you had a way of doing some pure counting thing, right? You've got more stuff, a little bit more stuff to do tomorrow, right? Ed has already left. Okay. Ed is still here, but Ed is on mute.
I've been talking, but I was muted. Yes, I do. And I've got also good ways of doing estimates that are much more exact.
Okay. Van. Okay, so just make sure that you have, I'm going to send you this file just so that you have it.
Good. I was going to ask for it.
Actually, yeah, okay, so count Wolfram model rules should probably have an exact form and an estimate form.
Okay.
Okay.
Is there a good person for statistics?
What kind of statistics?
You've got 1 billion elements. You sample 100,000 of them. You get 55 back. How good is the estimate?
Ask Gosha K.
Gosha, okay.
There are 2 Goshas. You've got to pick the right one. Actually, they're both, yeah, they both have Polish last names, so you have to. It's Gosha K.
Okay.
There are other people in the statistics team too, but I think she's probably a good one to ask.
Oh, I've got to do the connected estimate. That's a new one. Okay. All right. I'm going to let you go.
Thanks a lot, Ed. Well done. Okay. Bye.
Yeah.
Okay. Jonathan, hello.
Hi.
Right. What have you been up to? Okay. Element-wise, causal should still be functions. I don't think so.
Yeah, I don't think so either. I mean, we might use them internally for generating causal graphs efficiently, but we can simulate everything by just calling causal graph and setting include state ID to be true.
Right. So you've gotten all this stuff to work. Is that a true statement?
Yes. With one key caveat that I was keeping secret.
Yes.
Which is, I know you've been saying I've been complaining that the multi-way system notebook is kind of impossible to maintain for a while. So I'm doing all of this in my own multi-way system package, which is now, I think, feature equivalent to the multi-way system notebook, but in my opinion, much cleaner. But which we can turn into a function repository notebook.
Can I see it?
Yeah. Do you want me to put it on Dropbox, or should I just share it?
Sure, put it on Dropbox and with a -JG or something.
Okay.
Really feature equivalent? Everything?
Maybe not quite.
Well, that's the problem, right? What does it not have? Because then we're going to be all messed up, right? Does it have all the different cases of all the different ways you can enter the rules and things?
Yeah, I need to make sure that it's actually that what I said is actually true. But
Okay, well, let's see what you've got.
sure, hang on. Do you mind if I share for a moment?
Go ahead.
Okay. So if I do that, okay. Okay, so for instance, this is what I was saying before about well, hang on, if we do
You don't need to include event ID, right? That's irrelevant.
No, we don't. So yeah, I'm going to remove any reference to event IDs.
But just remove it from your input here, just so I don't get confused.
Well, actually, if you do that, I need to rewrite something to make sure
Okay,
that
okay.
if I
but
remove
now
it
those,
here,
for example, those events are not correctly rendered, right?
Right.
So how did that? So something went wrong there.
Right. And hang on, wait. Let me just check. Are they correctly rendered without?
No.
I've probably just not fully ported the event function, the event rendering function. So yeah, so this is the unmerged case, and we can recover the merged case by just removing that option. So I
Show me the unmerged case again.
Yep.
That's nice.
So if we do something like that. So yeah, so the complicated bit is figuring out effectively how you reconstruct the event information given only half of the required input, right? Because you know the input state IDs, but you don't a priori know the output state IDs. But you need both to reconstruct the event in the most general case. So I've had to change how the event application and event functions work, and that will have implications for how we do event selection and things. I think the upshot, though, is that it's going to make the event decomposition for the Wolfram model case a lot easier, I think.
All right. So you've got some more work to do here, but for goodness sake, test all the cases, right? I mean, can I see the code just to
yeah, it's over here. I mean, it's...
Is it much shorter, or is it about the same length?
I think it's shorter because I've removed some of the duplication, not all of it, but a lot of what was duplicated in the...
Can you go up to the top?
Yeah.
Okay, so that's a lot of the old stuff there.
Right. I mean, yeah, so the different cases for different input formats and things is largely the same.
Okay, and so you've got the list cases and things are done too.
Oh yeah. I mean, that's just as a structural point, I'm separating out each case so that all the string stuff is at the top, all the list stuff is in the middle, and so on.
Okay, so the list stuff. So you've got list evolution. Good. This is nice. This is good.
Right. And as Max and I were discussing this earlier. So because this is now in a package, it means I can integrate this as a pull request into set replace, which means I can write unit tests using the set replace stuff to make sure that we don't break anything.
That's good.
Which was, I think the multi-way system notebook could have used some unit tests.
Sure. Okay. But now practical. Okay, let me be very, very practical about this, because I'm trying to, at this point, I'm going to hit that section again in probably 24 to 48 hours, I think.
Okay. So what's the highest priority?
I can't remember anymore. I mean, I think it was that I needed this because we needed to generate some pictures based on this. So the two things that I know I'm going to hit are some of this stuff, and I can't remember exactly what it was now, together with the Wolfram model case.
Yep. Okay. So I can. Yeah.
Well, I don't know how realistic it is to finish it in 24 hours, because it needs to be finished first, and then we need to review it and write unit tests and so on.
Right. But
well, I'm perfectly happy to run it without that, okay? Because I've got some simple cases to do. They'll either work or they won't.
Okay, I mean, I can get the code to the point where you can produce some pictures within 24 hours. Whether those pictures will correspond to reality, as Max says, is another question.
Yeah, but they have to got to have things like the event rendering function working and so on.
Yeah, no, I mean, that'll be a simple fix.
Right. I mean, I think, look, I could, in terms of my path here, I mean, I could do the manifold section first. Okay, I may take a cut. I mean, look, the sections that are currently on the frontier. One is the section on typical behavior, which is the thing I've been working on right now. I was working on the last two days.
Right.
Then there is the section on then there's the manifold section, okay, for which I feel like I know what I want to say about geometric group theory and God knows what else, okay? The main thing that I'm upset about is that right now I'm going to say, oh, there isn't there's no very natural way to get these manifolds. You have to do a little bit of rule engineering to get the manifolds. I mean, to get manifolds we recognize. It's easy to get things that are right. Now, I mean, in a sense, that's not terribly surprising. I mean, in a sense, I even think that might be good, but it's a little surprising given that in the alternate model of the, oh, by the way, I think these design d'enfant, in my very poor French accent, these things, I believe, are closely related to cyclic, to the cyclic graph stuff that we invented, the colored network stuff that we invented a decade or so ago, more than a decade ago. Oh God, 15 years ago. Right, so the stuff that those colored network things, Max played with them at one point. You know what I'm talking about, Max?
I played with oriented ones, which are not the same as colored ones. But
really?
Yeah.
What's oriented? What do you mean?
The ones I was doing the first two summer schools were oriented ones, meaning that it doesn't matter. I mean, if you look at the ports, you cannot flip them. So 1, 2, 3, 2, 3, 1, and 3, 1, 2 are equivalent, but they're equivalent, so they're not colored. In other words, if your graph is planar, you can flip, you can rotate the vertices, but you cannot flip them upside down.
I see. We should describe that stuff because otherwise, I mean, it's somewhat useful because I've forgotten the history of this. I mean, I think we had those ones and then colored ones were invented subsequently. Is that right? To your knowledge?
No, it's the other way around. Well, actually, I don't know when. I mean,
I can go look.
Who invented it and when? But I was working on oriented ones much after the colored ones existed.
Okay. Well, Todd and I invented the colored ones back in probably 2004, maybe.
Okay, well, that was 10 years earlier.
That's so depressing. By the way, I was reading what the NKS book says about all this stuff. It's surprisingly sensible. I mean, there's very little in there that I think is sort of nonsense now. And I also realized, to my surprise, you realize there's 100 pages in the NKS book about all this stuff? I had not remembered there was nearly that much stuff. And there's 40 pages of notes. Anyway, it's kind of depressing. It's been 18, how long has it been? It's been nearly 18 years.
Well, it's depressing to me as well, because it was 5 years since the first summer school. And
that's less than 18, Max.
I know, but you did a lot of stuff during this 18 years, and I didn't do anything.
Well, I think you've become a better programmer, and you've also
a bit.
I wouldn't be. Yeah, well, make up for it now. all right. I hope. I mean, yeah. Okay. All right. So Jonathan, after he's got some sleep, can try. What? Oh, by the way, what happened to the weighted multi-way systems? Did anything happen to those?
I don't. Did we ever agree a design on them? For them?
I think we agreed we have something in the documentation.
Okay, I'll double check. If we have a design, I'm happy to implement it.
Right. I think it's now much easier to implement because you can now just trace through. Well, actually, it's yet another data structure around states, right?
Mm-hmm. Right. Yeah, I mean, actually, so now that we have this capability, there are a few things which I'm not entirely convinced we need still. So things like, the evolution graph versus the states graph.
Oh, no, please leave those. Those are very useful. Evolution graph I use all the time, and states graph I use all the time.
No, I understand, but the evolution graph is just the states graph with step numbers and state IDs included, and then with a layered graph plot.
Fine. You mean implementationally we could change it?
Well, implementationally, yes, but also, I mean, for the same reason that I don't think it makes sense to have the element-wise causal graph steps unmerged, I'm not entirely sure it makes sense to have two separate functions here.
No. We really need them. I've been using them. Trust me, I've been using this function, right? I use those two things all the time.
No, I understand, but you don't need to have separate cases for them anymore.
But yes, I do, because I don't want to set 16 options to get from one to the other.
Okay, fine.
See what I'm saying? I mean, it's just a usability thing. The other things, those element-wise things, which I never really understood very well to begin with, those can go, presumably. I've never used those because I didn't really understand them.
Right. So in Max's causal graph generation code, they're used internally, but I don't think we need to provide a sort of forward-facing access to them anymore.
Fine.
Because we can reproduce them.
Right. Okay.
So I'm going to prioritize. So in terms of just like meshing with your exposition stuff.
Yes.
I'm going to prioritize. I get things like causal graph, evolution causal graph, causal graph instances and things. Getting those working and having the rendering nice.
Yes, please. And some of these new features, yes, and some of these new features, I'm afraid I just don't remember the exact roadmap of what features I need. I mean, we can go and look at the actual text, and you can probably figure that out, but I just don't remember.
Sure. Well, I mean, if you send me, I'll have a look. But if there's anything you figure out that you need,
fine, I will let you know.
Otherwise, this multi-way system has a long tail of things to work on, and
does it? Okay, fine. Yeah, well, fine. I mean,
it'd be good to have a priority list at least.
Yes, I mean, I think that this. I mean, I hope. Yeah, I think we're going to go on using this thing because I think we're going to end up with all kinds of examples and cases and so on and so on and so on. So I'm not too worried about putting time into making this production grade.
Yeah, right. I agree. I think it's about time.
Right. Yeah, but I mean, I think, yeah, right. I mean, it's clear from all the things we've been doing with it and getting confused about things and so on and so on and so on. All right. Great. Okay. And I guess the roadmap after that, I don't know what, with the manifold stuff, I think it's mostly just going to show a bunch of examples and show how to compute dimensions and show various other kinds of things you can compute on a graph. And that's about it. And the rest will be left post-launch for the post-launch period. All right, great. Go to sleep.
Right.
Yes,
okay.
Sorry to keep you up so late.
No problem. Okay.
Okay. See ya.
Thanks. Talk to you soon.
Bye.
Bye.
Okay. I think I'm going to go to work on this enumeration stuff. So I think that's where we're at. So I was hoping, so from you, the main things of interest. So you've given me something for that. What am I saying? For the
generations coloring.
Yeah, generations coloring. And then the other thing is different updating orders.
Yeah.
Because
yeah, I know.
Okay. What updating orders do you think we can easily support? A random one, or I mean, if it's random, it'd be nice if it was seedable. I mean,
well, it definitely should be.
Okay.
Otherwise, it's not reproducible.
Well, quite.
Yeah. So I think I at first will just implement it for C++ case, especially since we are not doing disconnected rules anymore.
Yeah. No, I
and
agree.
then in C++ case, it's pretty easy to other things as well.
Okay. Well, what else do you want to try doing? I mean, we could try
well,
doing.
We can change priority on the sorting we already have, like least recent first, or oldest first, or take a rule index first, and so on.
Please do some of those. Please do them. The sooner you can do them, the better, because I want to find out how robust our results are to any of that stuff.
Yeah. But I think I'll start with a random one.
Fine. That's fine. And then we'll see what happens. I mean, I have a feeling that some of these things will just go to hell. I mean, they'll just be completely changed. But we'll see.
Yeah, they probably will be. The only thing, we still don't have check for complete generations and so on, which is more significant if we are going to do random evaluation of that.
Yes, because we'll end up with skewed generations. Right. I mean, are any of these other updating
So maybe
schemes?
I should work on that first. I mean, I don't know.
Yeah, but what about, is there another updating scheme where you can also get complete generations fairly easily?
No. It's pretty fundamental. The least recent first is what does it generation by generation. There are few parameters after that, like which permutation we use versus the rule index and so on. But those are pretty. I mean, in most cases, I wouldn't change anything.
Right.
And if we change least recent first to something else, then generations would be completely different.
Right. Okay. All right, I'm going to go and go on with this enumeration stuff, and I'm go back and redo the stuff I did earlier, because now we're dealing with these right-hand side rules, and I think you didn't give me this formula for this case, the case of right-hand side disconnected. Right, that allows.
I don't know. So what does it?
This is just estimating the number of distinct elements that you can have. Right?
I understand, but why is there no separate left and right hand side? What is
It
I?
doesn't matter. I can run over both left and right hand side because it doesn't matter.
Okay, well, that's not going to work if.
I know that. So that's why I was asking for the formula.
Well, okay, so left hand side is the same.
I know that.
And right hand side doesn't have minus ones.
And there's a 1 plus. Okay, so
let me think with 1 plus. I think 1 plus. Let's see. We still need to connect right hand side with left hand side, so that's.
-1, which would cancel this +1. So I think +1 goes away.
Okay. So this one, how do you make an underscript box? Do you realize I have not used this in years?
I think it's Control-4.
Yeah, I figured that out.
Okay.
Yeah, I got it. Okay, I think that's it for now. Let me just go to work here. And yeah, excellent. All right. Okay, to be continued, I guess.
Okay.
Okay.
See you.
Okay, bye.
Bye.